Can you hear me now, Shana?
Yeah, thanks.
Good, good, good. Oh, sorry for that. Okay, that was not good. Okay, were you able to follow so far? So essentially, it's these calculations lead you essentially to the R. I will record this again. Okay, so we essentially have now an equation. Oh, Marcelo, you had a question.
No, I was about to say that.
Oh, okay, thank you. Okay, so essentially we're looking at a slope that determines this function. Let me just put this on transparent. This is gonna... Okay. Yeah, so essentially we have now a slope, we have an intercept, but we will talk about this in more detail next time. And the R squared, absolutely correct pointed out, is in essence nothing else but the squared correlation coefficient. This is consistent with these values. This is only true when you're working with two variables. We will next time also talk about multivariable regression, where this is not true. And this is to be kept in mind. So this is only true when you have two variables. Otherwise, it's not correct. Okay, so this is the R squared. This is the slope. This is the intercept. This will be regression. That's the menu for Monday. Okay, so this is the scatter plot. Always good to kind of graphically depict your data that you have already an idea about the correlation and what you're gonna see numerically. So these correlations we did these calculations, and we're coming to the sum of squares. And essentially we have the sum of products of the deviations for each variable divided by the square root of the products of the sum of squares for each variable. And so there's a standardization included. So it subtracts this mean of each score from, it subtracts a mean from each score, and by that captures the variability. And as I said, the denominator is then being determined by the sample size. So the sample size will decrease the denominator, and by that, the R, the resulting R, will increase because it's divided by a smaller number. Bless you. Any questions to that? Just considerably. It's simple. In bigger picture, it's simple. And we did most parts we did in some shape or form we did already. Okay, partial correlations quantifies now the degree of association between two variables that remains when the correlations of these two variables with the third variable are mathematically eliminated. And this goes now in the direction. So if you have the risk of drowning or the number of drowning events and the number of ice creams consumed on the beach, essentially you will have a third variable, which is temperature, that will reduce this correlation between those two. And this is what essentially is quantified here again. And this is this DAG, this directed acyclic graph, where you have the third variable taking out this association. It removes or it diminishes the association between A and B. So all three need to be scale variables, and the correlation coefficient is essentially only the leftover that is left after subtracting the association with the third variable. We're not going to do this, but essentially this is a so-called Venn diagram, which depicts this overlap. We have a correlation between longevity in years and weekly hours of tennis. So, yeah, so the longer you play tennis, the more hours of tennis you're likely going to play or you have played. Years of education will associate longevity in years and will also affect your weekly hours of tennis. So now you have an overlap between this and this, this and this, this and this. And here you have B, which is the resultant. So essentially you have an association between A and C, which is longevity between weekly hours. You have weekly hours and years of education. That's A and C. And then you have B as the resultant. This is the leftover association. And this is your actual association that you see between exposure and outcome. And this is what I said before, right? So this is A, B, and C. So this is how you would look at this. And this is essentially what you do in epidemiology. You do it with the so-called mediation analysis. So these are A confounders, and then you have mediators that are in, and the difference is whether it's in the causal pathway or not, or whether it's just an association that affects both. And you can arithmetically approach this. You can arithmetically quantify what the leftover association between A and B is, but you will hear more about this in future steps of your education in that regard. So all three variables are measured. All three need to be scale variables. And it is calculated to express the association beyond the association of just one with another. So you're basically going by subtracting the third variable and the association of the third variable from the association between the primary two variables. And by that, you get the actual true correlation coefficient. That's what they mean. Yeah. Any questions to that? That's a little heavier, but it's essentially don't try to grasp the concept. So numerically, we're not going to approach this. We're not going to do this, but it's important to keep the concept in mind. To understand that there are third variables that will essentially have an effect on the numerical value of the primary association. Good. So correlation in psychometrics. So psychometrics is not my forte. So these are surveys, questionnaire, everything where you have a psychological assessment of somebody's health, somebody's physical functioning, somebody's well-being, somebody's general health, somebody's mood. So there are like a plethora of different survey topics. There are different questionnaires out there. It's quite complicated to essentially develop them. It's even harder to validate them. Then you also got to keep in mind, you got to sometimes tailor your questionnaires to certain populations. You need to also take into account that maybe you also need to alter your questionnaire for certain cultures, for certain languages. This is the step of validation. So when you have a questionnaire, you will always have to validate your questionnaire for the very reason, because in different languages, things may have different terminology. They may be perceived differently or also be perceived in different cultures. You don't know. So you need to always validate for the population you're using a questionnaire on. And this is the science of psychometrics. And psychometricians use correlation as one potential tool. I don't think it's the strongest tool, at least I don't hope so, because method comparison with correlation is a little bit complicated. That essentially examine two different aspects of the development of such measures. This is reliability and validity. And we talked about this already, right? Bless you. We talked about reliability in the context of retest reliability. You remember that was it the first or the second class? We talked about whether you want to quantify something the first time and you want to quantify the second time. The retest reliability will basically be high when the outcome of the second assessment essentially is comparable to the first one. So this is one way to quantify the reliability of a questionnaire. You can also do this. So this is retest reliability. So you need chronological order. So you do it the first time, you do it the second time, and you see whether this assessment is founded. A second way to assess reliability has nothing to do now with test retest. It's just generally to get a feeling of how reliable is my test. You basically have a questionnaire, and all questions in that questionnaire mean to address one question, mean to answer one question. If you're taking all the questions in that questionnaire, which is usually the terminology is you call them items. So you take all these items and you basically take the odd number and the even number items, and you basically split them in half. And you make a subset analysis of only the even number, you compare them with the outcome of the odd number. If this correlates with each other, and there's a high level of correlation, you can say, okay, so my survey is kind of consistent in bigger picture. So all the items kind of point out the same outcome. And the even more sophisticated way of assessing this, and this is also, it's using also a split half correlation, but a little bit more sophisticated. It's basically taking random chunks of this and basically compares this to the other chunks. Taking then the average of these correlations and quantifies overall, is the survey in its entirety asking or questioning one particular outcome? So is the outcome of this assessment, of this survey, of this questionnaire consistent? And it's called internal consistency, and is quantified with a coefficient alpha, also labeled as Cronbach's alpha. That's a very important one, because whenever you develop a questionnaire, you will actually use Cronbach's alpha as a marker of your reliability. If your questionnaire actually really questions what you mean to question, does it actually make sense? And this is, as far as I recall, on a scale from 0 to 1, and 0.75 is considered to be a reliable questionnaire. But I think there's a little bit of a debate what's acceptable. 0.75, I think, is a conservative estimate. So, but there's a certain mark of what reliability is acceptable for your questionnaire. Any question on that? And last but not least, we're going to talk about, so we had reliability, retest reliability, and the split half reliability, or the Cronbach's alpha, the reliability of the test per se. And secondly, we're talking now about validity. This is basically, is your questionnaire really asking what it means to answer? Is the outcome of your questionnaire really quantifying what you need to quantify? And this is something which you can quantify by associating with known measures or known clinical characteristics, known demographics, or whatever outcome is also determined by other factors. So basically you correlate the outcome of your questionnaire with any other data you have of your respondents. And by that, you basically get an idea whether this really points towards that outcome. So if you want to quantify general health, for example, and you have a questionnaire with, let's say, 20, 30 items, and you quantify how well does this respondent feel, and you're associating in your 20, 30 respondents, you're associating that with the number of hospitalizations the individual had over the last half year, and there's an association, you know that your general health questionnaire is to some extent reflecting how does that individual feel and how sick or how many comorbidities does this individual really have. So that's kind of the idea of validity. Make sense? Any questions? And lastly, and this is where they basically, so they have a little bit of a beef with magazine personality quizzes. They just mean to make the point that correlation can be used to establish validity of personality tests. But it's quite complicated to establish reliability and validity in real life. So these psychometric assessments we have in many journals and magazines around market effectiveness, they're not really too reliable or valid. And it's sometimes a little bit hard to really take them serious. So many of the questionnaires you will see in newspapers or magazines are not necessarily validated in any shape or form, and they're not necessarily really reflective what they mean to reflect. But yeah, we all have taken these quizzes. They're not necessarily something you should pay too much attention to. Yeah, but that's basically correlation, reliability and validity of tests and questionnaires. And as promised, it's rather short today. What's really interesting, and this will be the context of the next class, will be how to quantify that relationship, because regression analysis basically brings correlation and association to the next level. And this essentially is where you will see that you can predict, using this function, you can predict each y at each individual x entry. And this is where regression gets very, very powerful, when you really mean to predict an outcome. And this it's just very superficial, and it's just the first step, but it's a very powerful tool in the grid one. So since we have a little time now, we can actually also look at this in R. About the lab? Okay, we can always put that, yeah. Yes, the one is lab 3 and the other one is lab 4. Yes, and that's the solution. So okay, let's do that. Okay, let's go in the labs. So we have here practice lab 3. This was essentially the solution to the t-test example, right? So since we have 7 minutes, we can use that. That's actually good. Okay. So this is practice lab 3. So this was the comparison of exam outcomes. But basically, so we have here the same data as that we have discussed in class. Lab 4, lab 3 is, or no, let's quickly go through lab 3. And so this is just the t-test allows here to basically quantify it in a paired setting, exam 1 and 2. And this essentially will allow for you to quickly assign this to an object. So you can pack all of this in an object. If you do paired equals true, it will recognize it as a paired t-test. And essentially gives you here confidence intervals. And gives you here also the effect size. So this is lab 3 and lab 4 is a little bit trickier. So we open this too. So here you get the data frame 1 and 2. So data frame 1 is our ANOVA, right? This is the between groups ANOVA, the example of the dictator game. Then essentially we have data frame 2, that was the beer example. And with this code, so essentially you're doing here, and this code, I have included this code because it's from a package called dplyr, which is a very useful and very practically good package, allowing for you to essentially do descriptive statistics in a very simple manner. So you have, when you look at this code, it takes society, which is our degree of our data frame 1, which is the between groups ANOVA example. It will, and this little thing, the % greater than % is called a pipe. So it basically it's piping this data. So you have data frame 1, you group it by society. It basically it will lead the pipe to this function of summarize. Summarize comes from the prior package. It will give you counts, means, and standard deviations. And this is exactly what we have depicted here. We have counts, means, and standard deviations. This is just a very elegant way to summarize data. And that's why I included it, that you have that code at your disposition when you need it. So essentially, we're doing the same thing here. We have with the beer, we have again count, mean, and standard deviation. And this is now summarized by beer type. So we have here, that's data frame 2, and beer type. So we're grouping by beer type. Again, the pipe is summarizing the count, means, and standard deviations. And you get here the overview of cheap beer, high-end beer, and mid-range beer. So these are the means, the standard deviations, and the counts. When you want to change the level at which you're actually looking at it, you can also group it here, group by data frame 2, participant, with the pipe. You summarize it by count, mean, standard deviation. Again, you get it now on a participant level. So you have for each participant, you have the counts. So the tasted 3 beers. You have the mean ratings of each participant. And you basically get standard deviation within each participant. So that's the summarization step. So I know with the pipe it looks a little confusing. I know it's deploy is a little different. And then we can build the ANOVA model. And the ANOVA model is very simply only shown, simply called, by just using function AOB. AOB essentially will automatically recognize that you are trying to quantify the score as a function of society. So we have those 4 societies that we compared in the between groups ANOVA. And it will automatically quantify score as a function, and this is indicated here by the tilde. As a function of society. And by that, essentially, you can do an ANOVA table within seconds, where you actually get society as the group factor, and you get the residuals for each society. So you get degrees of freedom as 3. You get the sum of squares, which is consistent with the one we quantified. You get the mean squares, and you get your F, which is also consistent, and the associated p-value. And this is how simple you can basically build an ANOVA using R. If you want to do the same with a within group ANOVA, you need a different package. And this is a little tricky. So I played around with it. There are various different models how you can do that. So this was the best one I found. So you get the dependent variable here is the rating. The within group factor is beer. And the participant is basically the within group determinant. So you get, so you have DV within and WID, which is the participant ID, gets you essentially to an ANOVA table that shows you consistent results with what we quantified with our example. So there were no differences between the beers, but you can do then in pairwise t-test, where you essentially tell it to be true, you can actually compare the individual beer types to each other and the rating of these beer types. A little different for the ANOVA one, where you essentially get the Tucky honest significant difference test. You basically get these values here, where you have the confidence interval to compare the individual groups. And you have again the pairwise t-test. And these POST tests are basically looked at in the format of a grid. So basically farming and foraging here has no significant difference. It's at a p-value of 1. You can compare foraging to industrial, where you have borderline significance with like 6% p-value. And you can compare foraging versus natural resources, where you actually have a significant difference of smaller than 5% with a p-value of 1.3%. And this is essentially how you would pairwise t-test then the individual groups that you have quantified in your ANOVA. And it's consistent with what we've seen in our assessment. Does that to some extent explain practice lab 4 a little bit? Yeah?
That was really helpful, actually.
Hmm?
That was really helpful, actually. That was really helpful, actually.
Yeah?
Thank you.
Good, I'm happy. Happy to hear that. No, it's a little, I understand that starting off in R is a little bit complicated. I get that. But I think it's good that you have those codes. Maybe one day you will need them. All right, so we're at the end. Thanks for your attention and good job on the quiz. Any question from you, Shana?
Nope. Thank you so much.
All right. Have a good-
Good evening.